Today I'm going to talk about the transformation in industrial automation sectors driven by a move towards software-defined automation, the deployment of intelligent edge sensors, and seamless access to data. So hopefully over the course of the next 25 minutes or so, I'm going to take you on a journey through this transformation, what's driving it, what's happening under the surface, and how we will enable this through technology to get us there faster. So we're at a pivotal moment, really, when we look at the industrial automation sector, and it's a time of transformational change. So the pace of innovation has really accelerated. And traditionally, this is quite a traditional industry. So what we've seen is that, change can be very linear, very slow. But now it's actually a time of exponential change. And this is because innovation is actually compounding upon each other. So what we've seen in the past is, we've seen breakthroughs in computing power, connectivity, mobility, and it's taken up to a decade for these to become mainstream. But now, less than a decade, we can see some of this become, the norm. And that's because technological breakthroughs are really building on top of each other, and they're really shrinking the time it takes for them to get to market. So if we look back at history, what we see is, anyone want to guess, if you want a bit of audience participation, how many users the airplane got to in 70 years? How many users? Anyone want to shout out? Come on, we have to have one guesser. So it took 70 years for the airplane to get 50 million users. 14 years for the PC to have the same number of users, less than 3 years for the iPhone, and ChatGPT had 50 million users in less than 5 days. So that tells us about the pace at which consumers are adopting new products. And what that means is that for industrial systems and manufacturing systems, we need to have the agility to be able to respond to those changing customer needs. So how do we do that? And that's kind of the premise of today's talk. So what are the transformation levers that are really available to us on this journey towards software-defined automation? Well, first off, we have digitization. So that's all about capturing, digital data from across our factory, physical data, and turning it into digital information that we can use. And what you wouldn't actually believe is that a lot of manufacturing systems today still collect data manually, so process data, system data. So a recent survey by MLC, they're the Manufacturing Leadership Council, they represent a lot of the big global manufacturers in the US, said that 70% of their members still capture operational data in like a clipboard, an Excel file. So we hold in the palm of our hand a phone that connects us to the whole world. But that's not the world in the manufacturing world we live in today. So it's about creating digital-driven, fully connected data sources that enable us to visualize all of these data and make informed decisions. So what we get with all of this connected data is huge value, right? But also huge risk, because now all of our machines can talk to each other, they can talk to the enterprise cloud. So the attack surface in terms of cybersecurity becomes much bigger, and the severity of those attacks become greater. And other data shows us that 64% of industrial operators over the last year reported experiencing an OT, so an operating technology, cyber incidents. So it is a growing concern and a growing threat. So what do we do with all of this digital data? Well, one, we said we're going to visualize it to make better decisions. But two, we can use it to make these digital models or virtual representations of our factory floor. So maybe of our robot, maybe of our machine, maybe of our work cell. And what this enables us to do is to virtually simulate any changes we want to make in the virtual environment before we deploy them into the physical workspace. So we talked about we need agility. This is one of the biggest ways to get us agility, because now as we optimize for operational efficiency, the time we take down the line is much less. And while modeling was once the purview of, a nice to have or kind of an out there capability, now it's like a foundational element. And that takes us to robotics. So robots are, I suppose, the icon of the digital era, and I think there's some robots over here, and there's a humanoid somewhere else, I saw him. But thanks to breakthroughs in AI and machine learning and sensors, robots can now perceive their environment in real time, adapt, change, and learn. And that means they can take on complex tasks, or tasks that humans previously used to do. And why is this important? Because over the last 10 years, according to McKinsey, there's been 2.4 million vacant industrial jobs in the US. And that has cost the economy $2.5 trillion in GDP. So they're the dull, dirty, dangerous jobs that people don't want to do anymore. And we've even heard the CEO of Ford came out recently about all of these mechanical jobs that he doesn't have anyone to fill the recs. So underlying these four elements, we have AI. So AI, we've heard it all throughout the show, is foundational to a lot of the innovation in industrial automation systems. And we also have sustainability, because if we want to be able to make goods closer to the source of use in the UK, in Europe, in the US, then we need to become more productive. And what the data shows is we need to become 10x more productive than we are today. And we can only do that if we move to this data-centric type of operation. So my premise is that we need to move towards software-defined automation. And the question is, I suppose, why? So software-defined automation enables us to build in software, to scale it, and to distribute those innovations and breakthroughs digitally. So software-defined automation is all about abstracting the control logic, those critical control logic from hardware elements. So today, a lot of our automation systems, they're rigid, hardware-centric systems, so fixed function PLCs, proprietary protocols, they all equal long development cycles. We want to move away from static fixed systems. They served us really well. We could do high volume, low mix, make the same thing over and over, but they don't enable us to adapt to those changing customer needs we talked about at the start. So we need to move to these flexible automation systems that can interpret their environment, can make context-aware decisions, and can take optimal action on their own. So we need machines, or like robots or industrial systems, that can configure and be reconfigured in real time. And that is without changing any mechanics, without changing any hardware, without changing the electronics or any physical wires. So I'll give you an example. Anyone buy a six-pack of Coke or beer or anything at the weekend? Yes, yay. Okay, anyone buy a 12-pack or a 16-pack? So I guess when you are in a manufacturing facility and you make a bottling plant or a can-making plant, and they make a 6-pack, right? And then they want to change to an 8-pack or a 12-pack. What they do a lot still today is they have a mechanic or a technician who has to go down, and they have to pull these really high torque levers to change from making 6-packs to 8-packs to 10-packs. So you can think of the time lost in this, right? Somebody's having a tea break, then they have to get the tools, and they go down to the machine, on and on and on. We want to move to where we fit high torque motors, like simple stepper motors, onto these levers. We have centralized control that says change the levers to this position. Now we're making 6-packs. So this is all a saving in downtime. So what happens is your machine effectively becomes like the iPhone. It becomes a hardware platform. But the software, the intelligence and the feature sets all unlocked from central control through software. So we can change the operation by sending down software commands, and we don't have to change any physical hardware, right? That's the key. And what this fundamentally enables us to do is to make innovation more iterative, to become more agile, moving away from rigid hardware systems to responsive, intelligent systems that can have enable our factories to be more flexible. So we have to re-engineer and re-architect for agility. And when we look at that for a greenfield facility, right, so if you've got a brand new factory, it's kind of easy, right? You have a blank surface, you can, within constraints, do what you want. But we have a few things to think about. We need to have a scalable architecture. We need to have predefined reusable modules, right? And we need to think about our development process as a software development process. So where we would test virtually, where we would have versioning, and where we would deploy quick iterative cycles. The problem comes when it comes to brownfields, because we have a production line that we got to keep going, right? The money only comes in if we get the products out the door. So we have to have sympathetic and incremental modernization. And what that really means is we have to keep stable control systems operating, but we have to wrap them in a layer of decoupling and standardizations and data models and clever infrastructural changes so we can optimize branches under which we can still keep fixed function legacy running, and then over time upgrade those legacy systems. So we can do things like deploy more intelligent edge, non-invasive sensing, edge compute, standardized data models. But at the foundation of greenfield and brownfield, we're talking about the same thing. We want to move away from hardware-centric, move towards software flexibility, unlock productivity improvements, and ultimate agility. So this is, I suppose, the money slide where all the detail is, so you can bear with me. So I'm going to talk you a little bit through what's changing from right to left. So we've 4 key things, I suppose, or 5, that we really want to think about changing. So one is obviously decoupling our control logic from the hardware. 2 is we want to have dynamically allocatable I/O banks. 3, we want to have open protocols and standard data models. 4, we want to deploy more non-invasive sensing and robotics. And 5 is the OT-IT convergence. So I'll talk you through some of them a little bit on this slide, and then we'll talk through more as we progress. So the first one is, if you see here on right-hand side, we have fixed function centralized PLCs. And these have embedded, hard-coded control logic, where we move to the right, where we're abstracting the control logic into general-purpose software. And what this enables us to do is to actually run that as a containerized software, so we could run it virtually in the cloud. We could run it on an industrial PLC, which could be local, like a soft PLC. We will still need physical PLCs because timing in all manufacturing operations is critical. So we will have fixed function PLCs, but they will be software defined, and they will be distributed, so pushing intelligence down to the edge. The second one is a move towards dynamic allocations of I/O banks. So today, we've racks of I/Os in our factories, and they're all hardwired. So on this side, they're all hardwired links down. We want to move to the other side, where we have these I/O banks that we can configure through software, and they can be reallocated on demand and as our demand patterns change. And what this really opens up the door to is creating distributed or remote I/O functions. So here, what we can do is we can have elements of fixed function I/O, but we have an aggregation point, and that opens up a point where we can add localized edge intelligence, where we can add analytics, and we can add an element of diagnostics. Similarly, we want to deploy more Ethernet connected nodes, so IP addressability, which is really important if we want to be able to configure and reconfigure, so we can independently address every node on the network. And we could have edge switch aggregations, and this opens up the door to like network management, network insights, traffic insights. It's a good place to also look for cybersecurity because you can monitor changes in traffic patterns. Thirdly, we're looking at our open protocols. So software-defined automation depends on unified common data models. So semantic information that's totally hardware agnostic. And this enables us to share contextualized data across the network, so data all of our machines, everyone can understand, because it's shared contextual information, but it's not like tied to legacy systems, which tended to be proprietary, like Ethernet IP or Profinet. And that enables third-party algorithms or AI to be easily integrated, because we have open APIs, for example. And this is what enables true interoperability and plug-and-play nature. And finally, OT-IT convergence. So all of this is our operating technology layer. So it's timing critical. So it's everything that's controlled in the factory, the machines, the robots, the motors, the HMIs, everything. On our network, where we want to have seamless data exchange all up to the enterprise cloud, that might run our financial systems or our ordering systems, we have to have this seamless data exchange. And with that becomes the bigger risks, because OT networks were never really designed to be on the network, right? They were never designed to be connected to the internet. So fundamentally, when we move from fixed function, hopefully, to software defined, you see that we're unlocking adaptability. We're creating architectures that scale, not just scale within one plant, but can scale across multiple plants, so it's easier to replicate. And we're enabling this seamless data exchange. Okay, so when we just talked about that, the takeaway you probably think is, okay, we got to get rid of this fixed function hardware PLCs, but then we said we can't really get rid of them because we have to keep the stable operation going. What we find is the big problem is really unlocking standardized, contextualized data from these existing OT networks. So we can think of that problem in terms of three things. How do we access the data we have today? How do we create new data? And how do we act on that insights? And we have to act on it in a unified and consistent manner. So we want to deploy a network of sensors to capture data from across the factory floor. So first, access data. So this is about all of the existing data in the machines, which is all our measurement variables, but also additional information that's already on the instruments that we're not really necessarily capturing, which is additional maybe control data. And a recent survey by Siemens said that they estimate that only 20% of edge data in our factory is accessible today. So the challenge is huge, right? And then other data shows us that between less than 20, so between 10 and 20% of manufacturings claim they have full end-to-end digitization. So we don't have access to the data today, so that's not a trivial problem. And we have to look at how we upgrade the networks, and we'll look at that in the next slide. Two is we have to create new data. And how do we do that? Well, we have to deploy, obviously, networks of additional sensors, non-invasive, like condition monitoring type sensors, because software-defined automation to work, and all of our simulation models, who need to be real-time data-driven simulation models, need much richer data. They need multi-sensor insights, and that's enabled them to become predictive, and it also enables them to become autonomous. And then we move on to action. So how do we act on that data? And actually, before I move on, I'm going to give you one little example of creating new data. So one of the biggest users of energy in a factory is actually a motor. And we can deploy a servo drive to that motor today, and we could monitor the currents, which would be considered kind of control traffic running in that motor. So that would be maybe our accessing existing data. We can also deploy onto that motor a vibration sensor, a condition-based monitoring system, maybe also a temperature measurement, inertial measurement, and that would enable us new insights. So we could actually tell if the motor is starting to vibrate, we could tell if it's getting hot, if it's burning excess energy, if it's going outside its zone of normal operation. We can signal that and predict that it needs predictive maintenance. So instead of running that thing to fail, having weeks of downtime, we can take it down, maintain it, and then bring it back onto production. So that's an example of new secondary data. And that's also probably an example of acting appropriately on that data. So when I talked about the packaging machine, it was a good example of an adaptive control system. So we need to be able to use the data, analyze it, through machine learning, to have digital models, to have rules engines to determine what to do, and to be able to create configurable and adaptive control in response. So if we look at the data problem, we can summarize it into accessing the existing data, enriching the data in some way by additional measurements, and then acting appropriately on that information so we can drive change and adaptation in our production facilities. So I have a little bit of a deep dive on some of our connectivity and what in terms of connectivity is evolving. So the connectivity network is probably the backbone of any factory, and in particular of a software-defined automation system. And what we see in the connectivity networks is they're becoming inherently more complex, because now you have all of this real-time data, which is mission critical control traffic. So it has to arrive on time or within a bounded time of when it said it would arrive. And you have non-mission critical traffic, which is all those vibration measurements, all that additional information traversing the network. And they have to share the network in a way that makes sure control traffic does not get compromised. So for example, in my bottling plant, I send a command to stop filling my bottles. And it doesn't get there in time. I spill a load of my Coke or my beer, and I have to now bring down my production line. I have to send out people to clean it up. So I have a whole lost production time. What we need is that when those signals say they'll be here on a specific time, they will. So they're time-bound, they're deterministic, they're critical. And that becomes harder now because we've all of this additional diagnostics information traversing the network. So techniques like determinism, or TSN, enables this management of the traffic on the network, so time-critical signals always arrive when they say they'll arrive. The other complexity to our network is it's becoming hybrid. So we now have this mix of wired fixed function networks with wireless networks, and we have to be able to deal with that in a hybrid network. The other thing we have is more and more traffic, so more and more traffic traversing the network. Literally we have traditional field bus, RS485, it's not very fast, it just can't cope with all the data traversing it. So we need to move to Ethernet and gigabit type Ethernet links. And we also have a lot of machine vision now because of the advancements in AI for quality detection. And this is like multi-gig type Ethernet that we would need. And GMSL is a capability that's a really efficient way to capture camera data. But again, we have to optimize the network to support that because it can't go into traditional PLC systems. As we want to deploy more and more Ethernet nodes so that they're IP addressable, the ability to retrofit becomes important. So a new standard in terms of Ethernet, which is 10BASE-T1L, enables Ethernet to run over single twisted pair cabling, so it's easy to retrofit onto existing networks. And we also have binary sensors today, which are not very intelligent, so they're either on or off. We can deploy IO Link, which adds an element of intelligence to those low complexity binary sensors. And then, of course, private 5G. So what we see now is private 5G is a good option for wireless, particularly for high-density networks where you have a lot of sensor nodes or a lot of robots, AMRs. It's ultra-reliable and it's low latency, and it can be deterministic. So it enables us to do that management of control versus non-control traffic. I talked a little bit about dynamically allocating our I/O banks. And this is where we want them to be software configurable. So advancements in chip technology now has enabled a single chip that can do a software configurable channel that any port could be input, output, analog, or digital. And it can be software defined. And it's really power efficient. So what we've seen in the past is the racks, are quite beefy. We can make these rack modules very small now, and we can run full 8 channels without derating, so without having to maybe cool them from a power consumption perspective. It also enables this modular future-proofing. So we deploy a rack at 32 channels. We only deploy 8 of them. And as our factory expands, as we evolve, we can then configure the remaining channels. Okay, so we'll zoom back out and look at our full factory in its totality. And what we see is lots and lots of opportunity to deploy these sensors to capture new insights, but we also see lots of opportunities to deploy robotics. So moving around our graphic is a lot of AMRs or AGVs, and these are autonomous guided vehicles. And what they are is like little sensor hubs, little intelligence devices that are running around our factories and capturing environmental data. And they're comparing that data to localized stored maps that they have. And they're using that then to determine anomalies in the environment, so like a spillage, like a box that's in the way. And they then can automatically reroute to the best option, but they can also send that insight back to central control so we can have a human intervention. So for example, they know exactly where they were, where they saw that spillage, and they can say, hey, deploy the cleaning robot, right? Or if it's a box, they may not be able to interpret exactly what the box is, so they could deploy a more intelligent humanoid robot, for example, to go out and pick up the box. And that takes me to humanoids. So I have to update my picture because it doesn't have any humanoids on it. But what the humanoid will, I suppose, is it's really an embodiment of software-defined automation, because it's a really sensor-rich. It's got the advanced motion control, vision, embedded AI, all in a single platform. And sensor-rich and connectivity intense. And their human form factor, which is perfect for retrofitting into brownfield and legacy facilities, because you can see in a lot of those factories, space is a very, very constrained. So the humanoid form factor can fit in between narrow machines, it can traverse narrow corridors, and it can do a lot of manual, repetitive tasks that were previously done by humans. And one of the next evolutions we're going to move towards in terms of humanoids or even advanced grippers is this ability to get fine manipulation or dexterity. So they can interpret the object and pick it, but they can also maybe fine screws, because a lot of the tasks they're doing today are more repetitive. And we're also looking at capabilities to enable like human-like sense of touch. So like for slip detection, so if you have your phone and it starts to slip, you kind of know you need to add more pressure to hold on to it. And these are like the next evolutions that are going to come to enable humanoids to have more dexterity and take on much more complex tasks. So they are perhaps the key to the last mile in terms of automation. So that takes me to the conclusion, I suppose, of my presentation. So we started this session by talking about the pace of innovation has changed. It's bringing about transformations. It's causing us to move towards software-defined systems, deploy more intelligence, deploy more AI and sensors. And that's so we can create smarter, more resilient factories. And harnessing the combined power of all of these capabilities enables us to move towards software-defined approaches and become hardware agnostic. So we are capturing data and insights from across the factory floor, and we're using that to inform decision-making. We're deploying advanced automation and robotics to drive productivity. So we have a combination of data and automation, and this is what's unlocking in terms of agility, this move towards hyper-agile manufacturing, this ability to customize goods, to respond to customers' changing demand pattern. And it will enable us to make more goods closer to the source of use. So software-defined automation really, through combination of connectivity, configurability, and data insights, is going to unlock the level of agility and innovation we need to be able to compete, I suppose, in the manufacturing section at a global scale. Thank you.